Okay, so today we're going to be solving problem 5.37. Part A says a phonograph record of radius r carrying uniform surface charge sigma is rotating at a constant angular velocity omega. Find its magnetic dipole moment. So essentially what we're going to do is we're going to start with the dipole moment of a loop, but then we'll keep it in terms of little r so we can integrate over the radius over all of those loops, which will generate the disk. So to begin, the equation for the magnetic dipole moment, M equals to the current times the integral dA. In this case, the integrating over dA is going to give us pi times little r squared. That's that area of that disk. And it'll be pointing in the z hat direction as I have indicated in this picture. So now what we need to do is we need to find the current I in terms of little r. So we know that the current is equal to the linear charge density times the velocity. However, we don't have a linear charge density, we have a surface charge density. But we know that the linear charge density is just equal to the surface charge density times some element of length, dr. Also, it's important to note that we are given omega, not v. So we can say v is equal to omega times little r. And this will allow us to rewrite our current as being equal to equals sigma omega r dr. So now with these two pieces, we can then write the equation for our magnetic dipole moment equal to the integral from 0 to r of sigma omega pi times little r cubed dr, and that is in the z hat direction. These three terms, or that chunk right there, is constant, so we can just pull it out. So we will essentially get m is equal to sigma omega pi times the integral from 0 to r of r cubed dr z hat direction, which this is a pretty straightforward integral. And what we will end up getting is m is equal to sigma omega pi times big R to the fourth divided by 4 in the z hat direction. And that is part A. Okay, so part B says find the magnetic dipole moment of the spinning spherical shell in example 5.11, which I've drawn below. Show that for points r greater than the radius of the shell, the potential is that of a perfect dipole. So what we're going to do is something similar to part A, where we're going to start with this like shaded ring, and then we're going to put everything in terms of theta, so we can integrate over the surface, which makes that shell. So to begin with, the magnetic dipole moment equation is equal to I times the integral dA. Once again, we're going to get I pi r squared because we're using this ring in the z hat direction. However, little r, we want everything in terms of theta. So this little r is going to be r sine theta. And actually, this part right here is r d theta. That'll come into play in just a sec. So we can then rewrite this. M is equal to I pi r squared sine squared theta in the z hat direction. Okay, so the next step is going to be getting I in terms of theta. So we know we can write I as dq dt. But what is dq in this case? In this case, dq, we have this surface charge sigma times 2 pi r sine theta which is essentially the circumference of this ring, times r d theta, which is this element that I pointed out earlier right here. So for dt, we know that to make one full revolution, it goes 2 pi radians, and it's moving with an angular velocity omega. So we can say dt is equal to 2 pi divided by omega. When we combine those two, we can write our current as I equals sigma omega r squared sine theta d theta. Perfect. So now with those two pieces, we can integrate over theta, and we can rewrite our magnetic dipole moment equation being m is equal to the integral from 0 to pi of sigma omega r to the 4th pi times sine cubed theta d theta. And this is still in the z hat direction. Let me make sure yep, that's still in the z hat direction. And, as with part A, this is all constant, so we can factor that out. Sigma omega r to the 4th pi times the integral from 0 to pi of sine cubed theta d theta in the z hat direction. Okay, so to make things a little bit easier, I'm going to do this integral separately, and then plug the result back in. So we know that sine cubed theta can be written as sine theta times sine squared theta, which can then be rewritten as sine theta times 1 minus cosine squared theta. And this is setting up a u substitution. So then we can rewrite our integral as, or that portion of the integral, as the integral from 0 to pi of sine theta d theta minus the integral from 0 to pi of sine theta cosine squared theta d theta. Now in this case, we set u equal to cosine theta du is equal to negative sine theta d theta. And then when you integrate, you'll end up getting u cubed over 3. When you evaluate this full integral, you get cosine cubed over 3 minus cosine theta from 0 to pi. So now we can go ahead and evaluate, and you see that cosine cubed of pi over 3 is equal to negative 1/3 minus cosine of pi, which is just minus 1, minus cosine cubed of 0 over 3, which is 1/3, minus cosine of 0, which is 1. So this is 2/3 minus negative 2/3. So from this integral, we get 4/3. So we can then say our magnetic dipole moment, m, equals sigma omega r to the 4th times 4/3 pi in the z hat direction. So the last part of this question says, show that for points r greater than the radius of the shell, the potential is that of a perfect dipole. So First, because this is centered at the origin and pointing in the z direction, we can use the vector potential for a dipole equation, which is equal to mu naught over 4 pi times magnetic dipole moment times sine theta over r squared in the phi hat direction. And then we can go ahead and plug in our magnetic dipole moment and get mu naught over 4 pi times 4 pi over 3. And of course these will cancel. Times sigma omega r to the 4th sine theta over r squared in the phi hat direction, which just reduces to mu naught sigma omega r to the 4th over 3 times sine theta over r squared in the phi hat direction. So comparing this answer to the solution of example 5.11, we can see that this is the exact potential according to that example, meaning that there are no higher order multipole contributions. Essentially, the vector potential outside the sphere is exactly the same as a perfect dipole would produce.